The term parallel universe gets used casually, in films, in headlines, in everyday conversation, but physicists who study the structure of the cosmos use it carefully, and when they do, they mean something specific. Tonight's program covers 100 verified facts about what parallel universes actually mean in physics, where the idea comes from, what the mathematics requires, and where the science currently stands. The facts are drawn from quantum mechanics, cosmology, string theory, and the philosophy of science. No speculation has been added. Each fact reflects the current state of established or actively debated physics research. The term parallel universe is not a single scientific theory. It is an umbrella term covering several distinct hypotheses in physics and cosmology. When physicists use the phrase parallel universe, they are not referring to a single unified theory with one set of equations and one set of predictions. The term covers several separate scientific frameworks, each developed independently, each grounded in different branches of physics. Some of these frameworks arise from quantum mechanics. Others come from inflationary cosmology. Others emerge from string theory. Each one proposes, through its own reasoning, that physical reality may extend beyond what we can observe. What they share is the suggestion that our universe is not the totality of what exists. The term parallel universe holds these ideas together loosely, but treating them as a single idea would be a misrepresentation. Each framework has its own logic, its own predictions, and its own standing within the scientific community. Understanding the multiverse concept requires distinguishing between them rather than grouping them as if they were variations on a single theme. Physicists prefer the term multiverse to describe the broader concept of multiple coexisting realities. In scientific usage, the preferred term for the possibility of multiple universes is multiverse, not parallel universe. The distinction matters because multiverse is a more precise technical term used consistently across research literature to describe the broader framework within which individual theories of multiple universes operate. The word became widely used in the latter half of the 20th century and has since been adopted by physicists including Max Tegmark, Brian Greene, and Stephen Hawking, each using it in a somewhat different but related context. In all cases, the multiverse refers to the full collection of all universes that may exist, with our observable universe being one component of that larger whole. The term carries scientific weight that the more colloquial phrase does not, and it signals a seriousness of intent when physicists invoke it. It is worth noting that even researchers who use the term regularly disagree about whether the multiverse is a scientific prediction, a mathematical consequence, or a philosophical extrapolation from accepted theory. The multiverse is not science fiction. It emerges naturally from several well-tested and accepted branches of physics, including quantum mechanics and inflationary cosmology. The idea that multiple universes may exist did not originate in fiction, though it has appeared there extensively. In physics, the multiverse is a consequence that arises independently from multiple well-established theoretical frameworks. Quantum mechanics, which is among the most rigorously tested theories in the history of science, produces the multiverse as an implication of one of its major interpretations. Inflationary cosmology, which explains observed features of the universe including its large-scale uniformity, leads mathematically to the prediction of other bubble-like universes beyond our own. String theory, in its attempt to unify the fundamental forces of nature, generates an enormous landscape of possible physical configurations, each corresponding to a different potential universe. These are not peripheral ideas. They come from the same body of theory that underlies semiconductor technology, medical imaging, GPS navigation, and nuclear physics. The multiverse is a consequence of taking that body of theory seriously, not an invention introduced for aesthetic or narrative reasons. No parallel universe has ever been directly observed or detected. However, their existence is considered mathematically consistent with known physical laws. At present, there is no direct observational evidence for any parallel universe. No instrument has detected a signal from another cosmos. No experiment has produced data that requires the existence of other universes to be explained. This is a significant limitation, and physicists who support various multiverse theories acknowledge it plainly. What the science does offer is mathematical consistency. None of the currently verified laws of physics prohibit the existence of other universes, and several well-supported theoretical frameworks actively predict them as consequences of their own equations. Mathematical consistency is not the same as empirical confirmation. It means that the idea does not contradict what is already known, and in some interpretations the equations require it. The history of physics contains examples of predictions that were mathematically established long before they could be observed, including black holes, gravitational waves, and the Higgs boson. Whether parallel universes will follow the same path from mathematical prediction to observational confirmation remains an open question. The idea of parallel universes was first seriously introduced into modern physics in 1957 by American physicist Hugh Everett III. The modern scientific treatment of parallel universes began with Hugh Everett III, an American physicist who submitted his doctoral dissertation at Princeton University in 1957. Everett was 27 years old at the time. His paper proposed what he called the relative state formulation of quantum mechanics, a framework that would later be referred to as the many worlds interpretation. Everett's work was not a philosophical speculation or a thought experiment. It was a technical proposal aimed at resolving a specific problem in the mathematical foundations of quantum mechanics, a problem that had remained unsolved since the theory was developed in the 1920s. The physics establishment largely dismissed the paper at the time. Everett left academic physics and spent much of his subsequent career in defense and systems research. He died in 1982 without seeing his interpretation gain significant acceptance. In the decades following his death, the many worlds interpretation was revisited, expanded, and eventually became one of the most seriously discussed frameworks in the philosophy and foundations of quantum mechanics. Everett proposed his idea not as a philosophical thought experiment, but as a solution to one of quantum mechanics' most stubborn and unresolved problems. Hugh Everett's proposal of branching worlds was a response to a technical problem, not an exercise in speculation. The problem he was addressing is known as the measurement problem in quantum mechanics. Quantum theory describes particles as existing in superpositions of multiple states simultaneously. When a measurement is made, the particle appears to settle into a single definite state. The equations of quantum mechanics do not account for this transition. The theory provides no mechanism to explain why measurement produces one outcome rather than all outcomes. This gap had been noted since the 1920s and had been handled in the dominant Copenhagen interpretation by treating measurement as a special process outside the normal operation of the equations. Everett found this unsatisfying. His solution was to remove the assumption of collapse entirely and accept that all outcomes of all measurements occur, each in a separate branch of reality. Whether this solution is correct is still debated, but the motivation was technical precision, not philosophical expansiveness, and Everett's argument was constructed with the rigor expected of a doctoral dissertation in theoretical physics. The scientific study of parallel universes sits at the intersection of cosmology, quantum physics, and theoretical mathematics. Research into the possibility of parallel universes does not belong to a single scientific discipline. It draws from at least three distinct fields. Cosmology contributes the large-scale framework, observations of the universe's structure, its expansion history, and the physics of its earliest moments. Quantum mechanics contributes the small-scale framework, the behavior of particles, wave functions, and the measurement process. Theoretical mathematics provides the tools that both fields depend on, including differential geometry, group theory, and the mathematics of Hilbert spaces and manifolds. When physicists work on multiverse theories, they are typically combining results and methods from all three areas simultaneously. This cross-disciplinary nature makes the subject technically demanding and also means that progress in any one of the three fields can have implications for multiverse research. Advances in quantum computing, for example, affect how physicists think about the foundations of quantum mechanics. New measurements of the cosmic microwave background affect how cosmologists model the early universe and the conditions that may have produced other bubble universes. There are at least 4 distinctly different types of parallel universes proposed in modern physics, each arising from completely different reasoning. Physicists have identified at least 4 fundamentally separate types of parallel universe, each one arising from a different theoretical framework and each one making different claims about the nature of the additional realities it proposes. The first type involves regions of space beyond the observable universe in an infinite cosmos, where the same physical laws apply but different arrangements of matter may have produced different histories. The second type comes from the physics of eternal inflation, in which separate bubble universes form with potentially different physical constants. The third type comes from the many worlds interpretation of quantum mechanics, in which every possible outcome of every quantum event is realized in a separate branching reality. The fourth type, proposed by Max Tegmark, holds that every self-consistent mathematical structure corresponds to a physically existing universe. These four types are not related by degree. They are genuinely different proposals based on different physics. Conflating them as a single idea misrepresents the state of the science. Each one has its own advocates, its own critics, and its own standing within the relevant research community. Physicists Max Tegmark and Brian Greene have each independently developed their own classification systems for the types of multiverse. Two of the most systematic attempts to classify and distinguish multiverse theories have come from Max Tegmark, a cosmologist at the Massachusetts Institute of Technology, and Brian Greene, a theoretical physicist at Columbia University. Tegmark proposed a four-level classification system in which each level represents a different type of parallel universe arising from a deeper or more fundamental physical assumption. His Level 1 through Level 4 framework has become a widely referenced organizational structure in the field. Greene, in his 2011 book, The Hidden Reality, proposed a different classification consisting of 9 distinct types of multiverse, each defined by a different physical or mathematical source. The two systems overlap but are not identical. Both are intended not as definitive accounts but as frameworks for distinguishing ideas that are often grouped together without sufficient care. Neither system has achieved universal adoption, but both reflect a genuine effort to bring analytical precision to a subject that is frequently discussed in imprecise terms. The existence of competing classification systems is itself an indication of how contested and unresolved the underlying science remains. The existence of parallel universes, if true, would not violate any currently known law of physics. None of the verified laws of physics prohibit the existence of parallel universes. The conservation of energy, the speed of light as a maximum velocity, the laws of thermodynamics, general relativity, and quantum mechanics are all fully compatible with the existence of other universes. This does not mean those laws require other universes to exist. It means the hypothesis is not ruled out by what is already known. In physics, this kind of consistency is meaningful but limited. It places the multiverse in the category of ideas that cannot be dismissed on the basis of known physical law, while leaving open the empirical question of whether any version of the multiverse actually exists. Physicists distinguish between ideas that are consistent with known physics, ideas that are predicted by known physics, and ideas that are confirmed by observation. Parallel universes currently occupy the first category in general and the second category within specific theoretical frameworks. Whether they will ever reach the third category is not yet known. At the heart of quantum mechanics lies a deep mystery. Particles like electrons do not have fixed positions or states until they are observed or measured. One of the foundational and most extensively verified findings of quantum mechanics is that subatomic particles do not possess definite properties prior to measurement. An electron, for example, does not have a precise position in space until that position is measured. Before measurement, the electron's location is described by a probability distribution, a mathematical function that assigns a likelihood to each possible position. This is not a statement about the limits of measurement technology. It is a statement about the nature of the electron itself as far as quantum theory is concerned. The same applies to other properties such as momentum, spin, and energy. The particle exists in a range of possible states simultaneously, a condition described by its wave function. This property of quantum systems has been confirmed by decades of experimentation and is not in scientific dispute. What remains disputed is how to interpret it, specifically what the existence of multiple possible states prior to measurement implies about the nature of physical reality and what happens when measurement occurs. Before measurement, a quantum particle exists in a superposition, a blending of all its possible states at once. The term superposition in quantum mechanics refers to the condition in which a particle simultaneously occupies multiple possible states before a measurement is made. It is not a metaphor or an approximation. The mathematics of quantum theory requires it, and experiments confirm it. The classic demonstration is the double-slit experiment, in which a single particle sent through two slits produces an interference pattern on a detector screen, a pattern that can only be explained if the particle traveled through both slits simultaneously. The interference disappears when the particle's path is observed, indicating that observation itself alters the outcome. Superposition is also the basis of quantum computing, which exploits the ability of quantum bits to exist in multiple states at once in order to perform calculations that would be impossible for classical computers. The existence of superposition is not in question. It is the standard quantum mechanical description of particle states before measurement, and it is why the question of what happens during measurement has occupied physicists since the 1920s. When a measurement is made, the superposition appears to collapse into a single definite outcome, and no one fully agrees on why this happens. When a quantum system in superposition is measured, a single definite outcome is observed. This transition from multiple possible states to one actual state is called wave function collapse. It has been confirmed by experiment more times than can be counted. The electron that could have been anywhere in its probability distribution is found when measured at a specific location. That specific location is random, governed by the probabilities the wave function described, but it is singular and definite. The problem that has occupied physicists since the development of quantum mechanics is that the equations of the theory do not describe this transition. The Schrödinger equation, which governs the evolution of the wave function, is a smooth, deterministic equation with no mechanism for collapse built into it. Collapse is added as a separate postulate, not derived from anything more fundamental. Different interpretations of quantum mechanics handle this discrepancy in different ways, but no interpretation has achieved universal acceptance. The measurement problem, as it is called, remains one of the central unresolved questions in the foundations of physics. This collapse is called the measurement problem, and it has haunted physics since the 1920s. The measurement problem is the unresolved question of why and how quantum superpositions give way to definite outcomes when measurements are made. It has been present in physics since the quantum mechanical framework was established by Niels Bohr, Werner Heisenberg, and their contemporaries in the 1920s. The dominant early response to the problem was the Copenhagen interpretation, which treated measurement as a special process that simply produced collapse without attempting to explain the mechanism. This pragmatic approach worked for the purpose of making predictions, and quantum mechanics continued to produce accurate results across an expanding range of applications. But the interpretation left the measurement problem unresolved at a foundational level. Erwin Schrödinger's famous thought experiment involving a cat in a sealed box, simultaneously alive and dead in superposition until observed, was designed to illustrate the absurdity of applying superposition logic to macroscopic systems. The thought experiment was intended as a critique, not a proposal. It highlighted the gap between quantum mechanical description and physical intuition. That gap has not been fully closed in the nearly 100 years since it was identified. Hugh Everett's solution was radical. The wave function never collapses at all. Hugh Everett's 1957 proposal addressed the measurement problem by eliminating its central assumption. Rather than accepting wave function collapse as a given and asking how it occurs, Everett asked what would happen if it never occurred at all. He took the Schrödinger equation at full value, treating it as a complete and universal description of reality, one that applies to the measuring apparatus and the observer just as it applies to the particle being measured. Under this treatment, the wave function does not collapse when a measurement is made. Instead, it continues to evolve according to the Schrödinger equation, with all possible outcomes of the measurement remaining part of the wave function. The appearance of collapse, Everett argued, is what an observer inside one branch of the wave function would experience because that observer is now entangled with the measured system and can only perceive one outcome from within their branch. This proposal does not add any new equations or postulates. It removes the collapse postulate and accepts the consequences of doing so. Those consequences are the existence of multiple branching realities, one for each possible outcome of every quantum measurement. Everett proposed that every possible outcome of every quantum measurement actually occurs. but in separate, branching versions of reality. The core claim of Everett's many-worlds interpretation is that every possible outcome of every quantum measurement is physically realized in a separate branch of the universal wave function. When a particle in superposition is measured and could have two possible outcomes, both outcomes occur. The universe, in effect, divides into two versions of itself, one in which each outcome took place. Both branches are equally real. Neither is more fundamental than the other. The observer in each branch experiences only one outcome, because the observer has become entangled with the measurement outcome and can only access the branch in which they are located. The branching is not metaphorical. In Everett's framework, it is the literal consequence of taking the Schrödinger equation seriously as a complete description of physical reality. The number of branches produced by this process is enormous because quantum events occur at every level of physical interaction, including within every atom of every object at every moment. The total wave function of the universe in this picture is a continuously expanding structure containing all possible outcomes of all physical processes since the beginning of time. In Everett's many-worlds interpretation, when a particle can go left or right, the universe itself splits. One version where it goes left, one where it goes right. The branching described by the many-worlds interpretation occurs at the level of fundamental quantum events. When a quantum particle faces two equally probable outcomes, such as deflecting left or right when passing through a magnetic field, the many-worlds interpretation holds that both outcomes are realized. One version of the universe continues in which the particle went left, another continues in which it went right. Both versions are complete physical realities containing not just the particle but everything that interacted with it and everything that follows from those interactions. The split is governed entirely by the mathematics of the wave function. It produces no energy or information that would allow one branch to detect the other. From the perspective of an observer within either branch, the particle made one definite choice, and that is the only outcome they will ever know. This applies not only to controlled laboratory experiments, but to every quantum interaction occurring in every physical system at all times. In the many-worlds framework, branching is not an occasional event. It is the constant and universal mechanism by which quantum possibilities become physical realities. These branching universes do not communicate with each other. Once split, each version of reality continues forward in complete isolation. In the many-worlds interpretation, once a branching event has occurred, the resulting branches have no further physical interaction with each other. This isolation is not simply a practical limitation imposed by distance or energy. It is a consequence of decoherence, a quantum mechanical process by which the different branches of the wave function cease to interfere with one another as they become entangled with an increasing number of environmental particles. The process is effectively irreversible on any timescale relevant to human observation. Once decoherence has occurred, the branches evolve independently, and no signal or measurement from within one branch can access information from another. This feature of the many-worlds interpretation explains why, if branching is constantly occurring, we never observe its effects directly. The branch we occupy has decohered from all others, making them inaccessible by any known physical means. Critics of the interpretation sometimes point to this isolation as a reason to question its scientific status. If no branch can ever detect another, the claim that other branches exist may not be falsifiable in any practical sense. The many-worlds interpretation means that every decision, every quantum event, every coin flip generates a new branching universe. If the many-worlds interpretation is correct, branching is not limited to controlled laboratory experiments. It occurs wherever quantum mechanics applies, which means everywhere and at all times. Every radioactive decay, every photon absorption, every electron transition produces a branch. Physical processes at the macroscopic level, including coin flips, neurological events, and weather patterns, are ultimately governed by quantum mechanical interactions at the atomic and subatomic scale. Under the many-worlds interpretation, these processes generate branches as well. The number of branching events occurring within any ordinary physical system over any ordinary period of time is astronomically large, far beyond any number useful in everyday contexts. This continuous and pervasive branching is a feature of the interpretation, not an anomaly. It is the direct consequence of the Schrödinger equation operating without a collapse postulate. Whether this degree of ontological proliferation, the continuous creation of enormous numbers of equally real universes, is a strength or a weakness of the interpretation is a matter of active philosophical and scientific debate. In this framework, there is a parallel universe where every possible outcome of your life has already happened. Under the many worlds interpretation, every quantum event that played any role, however indirect, in producing an outcome in a person's life also produced at least one other outcome in at least one other branch. Because quantum mechanics governs the behavior of atoms and molecules, and because biological processes are ultimately molecular, the decisions, accidents, and contingencies of a human life are embedded in a chain of quantum events that, in the many worlds framework, produced multiple outcomes. There is a branch of the wave function for each of those outcomes. This is not a statement about free will or alternative histories in any narrative sense. It is a structural claim about the wave function, that every quantum possibility is realized in some branch, and that the quantum events underlying a human life generated branches in which things unfolded differently. The version of you in those branches is not hypothetical. In the many worlds framework, they are as real as the version experiencing this moment. Neither branch is more fundamental or more actual than the other. The distinction between what happened and what could have happened in this framework is a distinction between branches rather than between the real and the unreal. Everett's interpretation was largely ignored during his lifetime but has since become one of the most widely discussed interpretations of quantum mechanics. When Hugh Everett submitted his dissertation in 1957, the response from the physics community was largely dismissive. Niels Bohr, whose Copenhagen interpretation was the dominant framework at the time, did not find Everett's approach convincing. John Wheeler, Everett's doctoral supervisor, supported the work but acknowledged its difficulty in gaining acceptance. Everett made some revisions in response to feedback and then largely stopped engaging with academic physics. He spent the rest of his career in defense research and operations analysis. The revival of his interpretation began in the late 1960s, primarily through the advocacy of physicist Bryce DeWitt, who coined the name many worlds interpretation and promoted the idea in published papers. Interest grew further in subsequent decades as quantum information theory and quantum computing developed, providing new tools and new reasons to take the foundations of quantum mechanics seriously. Surveys of physicists conducted in the early 21st century have found that the many worlds interpretation is among the most popular interpretations of quantum mechanics, a significant reversal from its reception in 1957. David Deutsch, a British physicist at the University of Oxford, is one of the leading contemporary advocates for the many worlds interpretation. Deutsch is a founder of the theory of quantum computation and has argued that the many worlds interpretation is not merely one valid option among several, but the only interpretation of quantum mechanics that takes the theory's equations seriously without adding unjustified elements. His argument draws on the behavior of quantum computers. The exponential computational advantage of quantum computers over classical computers, Deutsch contends, can only be explained if quantum computations are being performed across multiple branches of the wave function simultaneously. In this view, quantum computers work because they exploit the computational resources of parallel realities. Whether this argument is persuasive depends in part on how one evaluates the relationship between computational models and physical reality, a question that remains genuinely open. Deutsch has made the case for this position in his 1997 book, The Fabric of Reality, and in subsequent technical papers. His advocacy has contributed to the renewed seriousness with which the many worlds interpretation is treated in contemporary physics. In the 1980s, physicist Alan Guth proposed cosmic inflation, the idea that the early universe underwent an extraordinarily rapid expansion in a fraction of a second after the Big Bang. In 1980, Alan Guth, then a postdoctoral researcher at Stanford University, proposed that the universe underwent a period of extremely rapid exponential expansion in the first fraction of a second after the Big Bang. This period, which he called inflation, would have lasted an extremely brief time but produced an expansion of space by a factor of at least 10 to the 26th power, with some estimates placing the expansion factor much higher. The proposal was not motivated by a desire to produce a multiverse. Guth was attempting to explain several observed features of the universe that the standard Big Bang model could not account for. Inflation was presented as a mechanism that could resolve specific empirical puzzles, and the mathematical framework Guth developed for it was grounded in quantum field theory. The inflationary period in Guth's model was driven by a scalar field called the inflaton, which occupied a high energy state and drove exponential expansion until it decayed to a lower energy state, releasing energy that reheated the universe and produced the matter and radiation that populated it afterward. Inflation theory was developed to explain several puzzling features of our universe, including why it looks so uniform in all directions. Cosmic inflation was proposed to address three specific problems in standard Big Bang cosmology. The first is the horizon problem. Observations of the cosmic microwave background show that the temperature of the early universe was nearly identical in all directions, even in regions that, given the age of the universe and the speed of light, could never have been in causal contact with each other. In standard Big Bang cosmology, there is no mechanism to explain this uniformity. Inflation resolves it by proposing that all of these regions were once in close contact and reached thermal equilibrium before being separated by the rapid expansion. The second problem is the flatness problem. Observations show that the large-scale geometry of the universe is extremely close to flat, which requires the initial energy density of the universe to have been tuned to an extraordinary degree of precision. Inflation naturally drives the geometry toward flatness. The third problem involves the predicted abundance of magnetic monopoles, hypothetical particles that certain grand unified theories predict should have been produced in large numbers early in the universe's history but have never been observed. Inflation dilutes their density to undetectable levels. The resolution of all three problems by a single mechanism was a significant argument for the theory's credibility. Inflationary cosmology has accumulated substantial observational support since the theory was proposed in 1980. The most significant evidence comes from measurements of the cosmic microwave background, the faint radiation that fills all of space and carries an imprint of the universe's state approximately 380,000 years after the Big Bang. The COBE satellite, launched in 1989, first detected the tiny temperature fluctuations in the CMB that inflationary theory predicts. These fluctuations, which are on the order of 1 part in 100,000, are thought to originate in quantum fluctuations of the inflaton field that were stretched to cosmic scales during inflation. The WMAP satellite, operating from 2001 to 2010, measured these fluctuations with greater precision and confirmed that their statistical properties are consistent with inflationary predictions. The Planck spacecraft, operated by the European Space Agency with data releases in 2013 and 2015, produced still more detailed CMB maps that continue to be consistent with inflation. The specific pattern of fluctuations observed, including their spectrum and statistical distribution, matches inflationary predictions to a level of precision that makes alternative explanations difficult to sustain. Inflation has not been confirmed beyond all possible doubt, and certain of its variants have been constrained or ruled out by observational data, but the core framework is broadly supported. One of the significant and initially unexpected consequences of inflationary theory is that the inflationary process, once examined carefully in the context of quantum field theory, appears to be self-perpetuating on large scales. The inflaton field that drives inflation is subject to quantum fluctuations. In any given region of space, these fluctuations can cause the field to decay to a lower energy state, ending inflation locally. But in other regions, the fluctuations can maintain the field at high energy, allowing inflation to continue. Because the regions where inflation continues are expanding exponentially, they rapidly dominate the total volume of space. The result is that while inflation ends locally in individual regions, it continues globally across an ever-expanding volume. This was recognized independently by several physicists in the early 1980s, including Paul Steinhardt and Alexander Vilenkin, and was developed most extensively by Andre Linde. The implication is that inflation, once started, does not end cleanly and completely. It produces an ongoing process in which regions of ended inflation, each constituting a separate universe, are continually being generated within a background of continued inflation. In the framework of eternal inflation, the universe consists of two distinct types of region. In the first type, the inflaton field remains at high energy, and inflation continues, driving exponential expansion. These regions cannot form the structures of ordinary matter because the expansion is too rapid for gravity to pull matter together. In the second type, the inflaton field has decayed to a lower energy state. Inflation has ended, and the energy released in that decay has reheated the region and produced the particles and radiation that constitute ordinary matter. Our universe is a region of the second type. When inflation ended in our region, the energy of the inflaton field converted into the hot, dense plasma that the standard Big Bang model describes. From that point, the physics of our universe proceeded according to the standard cosmological model: expansion, cooling, the formation of nuclei, the release of the cosmic microwave background, and the eventual formation of galaxies and stars. In the framework of eternal inflation, this process of local inflation ending and ordinary cosmological evolution beginning is occurring continuously in other regions of the larger inflationary background, each one producing what can be described as a separate universe. The concept of eternal inflation was developed primarily by Andrei Linde, a Russian-American physicist who was then working at the Lebedev Physical Institute in Moscow before later joining Stanford University. In 1983, Linde proposed what he called chaotic inflation, a version of inflationary theory in which the inflaton field starts in a chaotic, high-energy state across different regions of space. He subsequently recognized and elaborated the self-reproducing nature of the inflationary process, showing that under a broad range of conditions, inflation would continue indefinitely in the global sense while ending locally. Linde's work on eternal inflation established the theoretical foundation for what is now commonly called the inflationary multiverse. The essential result is that inflation is not a single event in the history of one universe, but an ongoing process that continuously generates new regions of space in which local inflation ends and ordinary physics can begin. Linde has continued to work on inflationary cosmology and the multiverse for several decades. His framework is one of the most developed and most widely cited approaches to the question of why our universe has the physical properties it does. In the eternal inflation framework, the regions where the inflaton field decays and inflation ends are referred to as bubble universes. The term comes from the physical model in which these regions nucleate within the surrounding inflating space, somewhat analogously to bubbles forming in a superheated liquid. Each bubble is causally isolated from every other bubble by the continuing inflation of the space between them. Within each bubble, the laws of physics are determined by the configuration of quantum fields at the moment inflation ended. The bubble evolves independently from that point, governed by whatever physical constants and particle properties resulted from that configuration. Our observable universe is one such bubble. Everything within our cosmic horizon, every galaxy, every star, every particle that has ever been detected or studied is contained within this single bubble. The bubble had a beginning when the inflaton field in our region decayed, and it has an evolution governed by the standard model of particle physics and general relativity. Other bubbles produced by the same eternal inflationary process are separated from us by regions of continuing inflation and are not accessible by any means available within our own bubble. The observable universe spans approximately 93 billion light-years in diameter and contains an estimated 2 trillion galaxies, each comprising hundreds of billions of stars. All of this, along with every subatomic particle ever detected or theorized to exist within it, constitutes what physicists mean by our universe. In the eternal inflation framework, this entire structure is a single bubble, one region among an indefinite or infinite number of regions in which local inflation has ended and ordinary physical evolution has proceeded. The other bubbles are not extensions of our universe. They are separate physical systems, each with its own history, each governed by whatever physical constants emerged when inflation ended in that region. The separation between bubbles is maintained by the continuing inflation of the space between them, which expands faster than any signal could travel. The boundaries between bubbles are not spatial boundaries in the ordinary sense. They are causal horizons, regions of spacetime that are permanently inaccessible from any point within our bubble. The claim that other bubbles exist is a prediction of the eternal inflation framework, not a claim that has been directly confirmed by observation. One of the significant implications of the eternal inflation framework, particularly when combined with string theory, is that different bubble universes may have different values for the fundamental physical constants. In our universe, quantities such as the gravitational constant, the speed of light, the mass of the electron, and the strength of the electromagnetic force have specific values that have remained constant throughout the universe's history and are uniform across space. In the eternal inflation picture, these values are determined by the configuration of quantum fields when inflation ended in a given bubble. Different configurations produce different values. Two bubble universes that formed from the same inflationary background but in different ways could have different gravitational constants, different particle masses, or different numbers of effective forces. The range of values is thought to be enormous, constrained only by the mathematical structure of the underlying theory, which in string theory generates a landscape of approximately 10 to the 500 possible configurations. Most of these configurations would produce bubble universes in which the physical conditions are very different from our own, and in most cases conditions that would not permit the formation of stars, atoms, or complex structures of any kind. Physicists have analyzed how the large-scale structure of the universe and the possibility of complex chemistry depend on the specific values of the fundamental physical constants. The results consistently show that the range of constant values compatible with a universe containing stars, stable atoms, and the conditions required for life is very narrow compared to the full range of values that are mathematically possible. Small changes to the gravitational constant would alter how quickly stars burn through their fuel, potentially making stellar lifetimes too short for planetary systems to stabilize. Changes to the strong nuclear force would affect whether atomic nuclei heavier than hydrogen could form, which would eliminate the chemical elements on which organic chemistry depends. Changes to the cosmological constant would affect whether the universe expanded at a rate compatible with structure formation. In bubble universes where these constants fall outside the narrow, life-compatible range, the universe would consist of structures far simpler than anything observed in our own. Perhaps a uniform gas that never collapses into stars, or a universe that recollapsed before any structure formed, or one in which atoms themselves are unstable. The causal isolation of bubble universes in the eternal inflation framework is absolute, given currently understood physics. The space between any two bubbles is occupied by the still inflating background, which expands at a rate that exceeds the speed of light. This does not violate special relativity, which limits the speed at which signals can travel through space, but does not limit the rate at which space itself can expand. Because the space between bubbles is expanding faster than any signal could cross it, no information can travel from one bubble to another. The two bubbles are permanently beyond each other's event horizons. This is the same principle that places distant regions of our own universe beyond our observable horizon. Not that they are too far away in a static sense, but that the space between us and them is expanding too quickly for light to bridge the gap. The difference in the eternal inflation case is that this isolation is total and applies to all possible forms of signal or interaction. There is no known physical mechanism by which one bubble universe could detect, measure, or communicate with another. Max Tegmark, a cosmologist at the Massachusetts Institute of Technology, has proposed what he calls the mathematical universe hypothesis, a framework that extends the multiverse concept further than any of the physical theories from which it more commonly arises. Tegmark's hypothesis is grounded in an observation about the relationship between mathematics and physics. The physical world is described by mathematical structures with striking accuracy and completeness, a fact that Nobel laureate Eugene Wigner referred to in 1960 as the unreasonable effectiveness of mathematics in the natural sciences. Tegmark's response to this observation is to propose that the relationship is not one of description, but of identity. In his framework, the universe is not merely described by mathematics, it is a mathematical structure. This is a philosophically radical position, but Tegmark has developed it in technical detail and has argued for it on both empirical and theoretical grounds. The hypothesis has attracted serious engagement from physicists and philosophers, though it also has substantial critics who question whether it is a scientific claim in any meaningful sense. The central claim of Tegmark's mathematical universe hypothesis is a distinction between two ways of understanding the relationship between physical reality and mathematics. The standard view in physics is that mathematics is a tool, an extremely effective one, for describing the behavior of a physical world that exists independently of mathematical description. In this view, the universe is made of physical stuff, and mathematics describes how that stuff behaves. Tegmark's hypothesis inverts this relationship. He argues that there is no physical stuff underlying the mathematics, no non-mathematical substrate that the equations describe. The mathematical structure itself is the physical reality. What we call matter, energy, space, and time are features of a mathematical structure, and the experience of living within that structure is what it feels like to be a physical entity governed by its rules. Tegmark supports this position with the observation that every known physical property of every known particle or field can be expressed in purely mathematical terms, with no remainder of non-mathematical content. He argues that if this is true of our universe, and if there is no principled reason to treat our universe as special, then all self-consistent mathematical structures should be equally real. Tegmark's hypothesis, if accepted, leads directly to a specific form of the multiverse. If physical existence is the same thing as being a self-consistent mathematical structure, then every self-consistent mathematical structure that can be defined is a physical reality. This includes mathematical structures that bear no resemblance to our universe. A mathematical structure with 17 spatial dimensions and no temporal dimension would be a physical reality in this framework. A structure governed by completely different symmetry groups producing entities with no analog in our standard model would also be real. The totality of all such structures constitutes what Tegmark calls the level 4 multiverse, the most expansive of the 4 multiverse levels he classifies. This is a stronger claim than the claim made by eternal inflation or the many worlds interpretation. Both of those frameworks produce additional universes with the same fundamental mathematical structure as our own, but different histories or different physical constants. Tegmark's level 4 multiverse includes universes with different mathematical structures entirely, making it a much broader claim about the scope of physical existence. Tegmark's hypothesis frames the existence of parallel universes not as a contingent fact about the world, but as a logical necessity. Mathematical structures do not require a physical cause to exist. The number 7 exists without having been created, without occupying space, and without depending on any physical process. In Tegmark's framework, if physical existence is equivalent to mathematical existence, then universes exist in the same way that mathematical structures exist, necessarily, without requiring a cause or a mechanism. This shifts the multiverse from a prediction to a logical consequence. Under the mathematical universe hypothesis, asking why parallel universes exist is analogous to asking why numbers exist. The answer, in Tegmark's view, is that self-consistent structures of any kind are simply real in the deepest sense of that word. Critics of this position argue that it blurs the distinction between mathematical objects and physical objects in a way that is philosophically problematic, and that the hypothesis may not be testable in any way that would allow it to function as a scientific theory. Tegmark acknowledges these concerns and argues that they do not constitute decisive objections. Within Tegmark's 4-level classification of the multiverse, the level 4 multiverse represents the most expansive possible scope. Each of the 4 levels involves a different kind of parallel universe arising from a different physical or mathematical source. The level 1 multiverse consists of regions of space beyond our cosmic horizon in an infinite universe, where the same laws of physics apply but different arrangements of matter have produced different histories. The level 2 multiverse consists of the bubble universes of eternal inflation, where physical constants may differ between universes. The level 3 multiverse consists of the branching realities of the many worlds interpretation of quantum mechanics. The level 4 multiverse consists of all self-consistent mathematical structures. Each level includes the previous levels as a subset. The level 4 multiverse contains all possible physical realities, not only those with laws similar to our own. Tegmark's classification is useful primarily as a framework for distinguishing different types of multiverse claims, and it has been widely cited in physics and philosophy literature, though the underlying hypotheses, particularly level 4, remain highly contested. The first 3 levels of Tegmark's multiverse classification are each grounded in a specific physical theory. The level 1 multiverse follows from the assumption that space is infinite or very large relative to the observable universe. In an infinite space governed by our physical laws, probability theory implies that every possible arrangement of matter within a Hubble volume, the observable region, must eventually repeat. This produces regions of space identical to our own and regions with different arrangements, all governed by the same physical laws. The level 2 multiverse follows from the eternal inflation framework developed by Guth, Lind, and others. In this level, different bubble universes may have different physical constants, determined by the configuration of fields when inflation ended in each bubble. The Level 3 multiverse follows from the many worlds interpretation of quantum mechanics. In this level, every possible quantum outcome is realized in a separate branch of the wave function. All three levels are grounded in existing physical theories that have independent support from observation and experiment. The Level 4 multiverse, which encompasses all self-consistent mathematical structures, is a philosophical extension that Tegmark has argued for on logical grounds, but which does not follow directly from any currently confirmed physical theory. The Level 4 multiverse, as Tegmark defines it, is not limited to universes that resemble ours in basic structure. It includes every self-consistent mathematical structure, which encompasses universes with different numbers of spatial dimensions, different fundamental forces, different symmetries, and different types of entities that have no counterpart in our physical experience. A mathematical structure with 2 temporal dimensions and 4 spatial dimensions would be a Level 4 universe. A structure governed by a completely different set of symmetry groups, producing particles and interactions unlike anything in our standard model, would also qualify. The Level 4 multiverse is therefore far broader than the multiverse predicted by eternal inflation, which produces universes with the same general mathematical structure as ours but different physical constants. It is also broader than the many worlds multiverse, which produces universes with the same physical laws but different quantum histories. The Level 4 framework raises philosophical questions about what it means for a mathematical structure to be physically real, questions that do not arise in the same way for the physical multiverse theories grounded in cosmology and quantum mechanics. The most significant scientific objection to Tegmark's mathematical universe hypothesis is that it may not be falsifiable in the standard scientific sense. Falsifiability, the principle associated with philosopher Karl Popper, holds that a scientific hypothesis must make predictions that could in principle be shown to be false by experiment or observation. A hypothesis that is consistent with all possible observations provides no scientific traction because no measurement could distinguish between its being true and its being false. Tegmark's hypothesis, in its most general form, is compatible with any physical observation because any observation is by definition occurring within a mathematical structure. This means the hypothesis cannot be ruled out by experiment, but also cannot be confirmed by it in a way that distinguishes it from simpler alternatives. Critics, including physicists George Ellis and Joe Silk, have argued that the mathematical universe hypothesis exemplifies a broader problem in contemporary theoretical physics, in which untestable ideas have increasingly been accepted into scientific discourse without meeting the traditional standards of the discipline. This is a substantive objection, and it applies not only to Tegmark's hypothesis but to several other multiverse frameworks as well. Tegmark does not dispute that his hypothesis faces significant testability challenges. He has addressed this objection directly in his published work and has argued for a distinction between theories that are unscientific and theories that are currently unconfirmed. His position is that the mathematical universe hypothesis follows from premises that are themselves scientifically motivated, and that a theory's current lack of testability does not place it outside the domain of science. He draws analogies to other theories that were long untestable before new technology or new theoretical tools made them accessible to experiment. General relativity was in some respects untestable for decades after it was proposed. String theory has not been confirmed experimentally despite extensive development. Tegmark also argues that his hypothesis does make a specific prediction that the fundamental structure of our universe should be expressible in purely mathematical terms, with no additional non-mathematical content. He regards this as a testable structural claim, though critics point out that it is extremely difficult to falsify in practice. The debate between Tegmark and his critics reflects a broader disagreement within physics about the criteria that scientific theories must meet and the role that mathematical consistency and theoretical elegance should play in assessing them. String theory is a theoretical framework developed over several decades with the goal of providing a single, consistent description of all fundamental forces and all matter. The primary motivation for string theory is the incompatibility between the two most successful theories in physics: quantum mechanics, which describes the behavior of matter at the smallest scales, and general relativity, which describes gravity and the structure of spacetime at large scales. Both theories are extraordinarily accurate within their respective domains. When physicists attempt to apply them simultaneously, as is necessary to describe conditions at the center of a black hole or at the moment of the Big Bang, the mathematics breaks down, producing results that are physically meaningless. String theory was developed as a framework that might resolve this incompatibility by providing a common foundation from which both quantum mechanics and general relativity could be derived as limiting cases. After several decades of development, string theory has not been confirmed by experiment, but it remains the most mathematically developed candidate for a unified theory of physics and has produced a substantial body of results relevant to both pure mathematics and theoretical physics. The central departure of string theory from the standard model of particle physics is the nature of the fundamental constituents of matter. In the standard model, elementary particles such as electrons, quarks, and photons are treated as mathematical points with no spatial extent. This treatment works extremely well for calculating the outcomes of particle physics experiments, but it introduces mathematical problems when gravity is included. String theory replaces point particles with one-dimensional objects called strings, which have spatial extent in one dimension. These strings can be open, with two endpoints, or closed, forming loops. The characteristic length of a string is thought to be near the Planck length, approximately 10 to the negative 35 meters, which is many orders of magnitude smaller than the scales accessible to current particle accelerators. Because strings are so small, they appear point-like in all existing experiments, which is why the standard model's point particle treatment has been sufficient for current purposes. The extended nature of strings resolves certain mathematical problems that arise in point particle theories, including the infinities that appear when quantum mechanics and gravity are combined in the standard framework. The mechanism by which string theory accounts for the diversity of known particles is the vibrational behavior of strings. A string can vibrate in many different ways, and each distinct vibrational mode corresponds to a different particle with different properties. A string vibrating in one mode has the properties of an electron. A string vibrating in a different mode has the properties of a quark. Another mode corresponds to a photon. This is a significant conceptual simplification compared to the standard model, in which different types of particles are simply different types of objects with no underlying explanation for why those particular types exist. In string theory, the diversity of particle types arises naturally from the different ways a single type of fundamental object can vibrate. One particular prediction of string theory is the existence of a massless, spin-2 particle among the vibrational modes. This particle has exactly the properties expected of the graviton, the hypothetical carrier of the gravitational force. The emergence of the graviton as a prediction of string theory, rather than something that has to be added separately, is one of the main reasons physicists consider string theory a promising approach to unifying quantum mechanics and gravity. String theory is mathematically consistent only when formulated in specific numbers of spacetime dimensions that are higher than the 4 dimensions, 3 of space and 1 of time, that we observe. In the original formulation of bosonic string theory, 26 dimensions are required. In the more developed superstring theories, which incorporate supersymmetry, 10 dimensions are required. In M theory, which unifies the 5 different versions of superstring theory into a single framework, 11 dimensions are required. These requirements are not adjustable parameters chosen for convenience. They emerge from the internal mathematical consistency of the theory. In lower numbers of dimensions, certain quantum mechanical anomalies arise that cannot be cancelled, and the theory produces inconsistent results. The requirement for extra dimensions is therefore a firm prediction of the framework, not an optional feature. The absence of observed extra dimensions at macroscopic scales is addressed by the assumption that the additional dimensions are compactified, meaning they are curled up into shapes of extremely small size that are undetectable with current experimental tools. The concept of compactification in string theory refers to the geometric process by which extra spatial dimensions are constrained to very small scales, making them unobservable at the energies accessible to current experiments. The idea was first proposed in the 1920s by Theodor Kaluza and Oscar Klein, who attempted to unify electromagnetism and gravity by introducing a 5th spatial dimension curled into a circle of very small radius. String theory adopts and extends this idea. The extra 6 or 7 dimensions required by the theory are assumed to be compactified into compact geometric shapes at length scales near the Planck length, approximately 10 to the negative 35 meters. Current particle accelerators, including the Large Hadron Collider at CERN, can probe distances down to approximately 10 to the negative 19 meters, which is roughly 16 orders of magnitude larger than the Planck scale. The extra dimensions, if compactified at the Planck scale, would be entirely invisible to any current experimental probe. The absence of evidence for extra dimensions at accessible scales is therefore fully consistent with string theory. However, this also means that the compactification assumption cannot currently be confirmed by experiment. In string theory, the physical properties of a universe, including the masses of fundamental particles, the strengths of the fundamental forces, and the values of the physical constants, are determined by the geometry of the compactified extra dimensions. The extra dimensions can be compactified in many different ways, producing many different effective four-dimensional physical theories, each with different particle content and different constants. The compact geometric shapes that the extra dimensions take in string theory are called Calabi-Yau manifolds. These are complex, multidimensional geometric objects that can be compactified with many different topological configurations, each producing a different set of four-dimensional physical laws. The specific Calabi-Yau configuration that describes our universe, assuming string theory is correct, would determine every measurable property of the particles and forces we observe. A different Calabi-Yau configuration would produce a different physics entirely. This is the mechanism by which string theory generates the enormous landscape of possible universes, each with different physical laws, that is referred to in the context of the multiverse. The number of distinct ways that the extra dimensions of string theory can be compactified is estimated to be approximately 10 to the 500. This estimate is based on analyses of the number of distinct Calabi-Yau manifold topologies and the number of ways that additional fields and fluxes can be configured within those manifolds. The estimate is rough, as the full mathematical landscape of string theory compactifications has not been comprehensively mapped, but it is consistently cited in the research literature as a lower bound on the number of distinct vacua. For context, the number of atoms in the observable universe is estimated at approximately 10 to the 80. The number of possible string theory configurations exceeds this by 420 orders of magnitude. Each configuration is a valid solution to the equations of string theory and corresponds to a different set of effective physical laws in 4 dimensions. Not all configurations produce universes resembling ours. The vast majority produce universes in which the physical constants take values very different from those observed in our universe, and in most cases values that would not permit the formation of atoms, stars, or any complex structure. The enormous collection of possible string theory compactifications, each corresponding to a different set of physical laws, is collectively referred to as the string theory landscape. The term was introduced and developed primarily by physicist Leonard Susskind at Stanford University, who has argued that the landscape, combined with the eternal inflation framework, provides the most complete scientific account available for why our universe has the physical constants it has. The landscape concept transforms the question of the uniqueness of physical law. If string theory is correct, and if the landscape contains 10 to the 500 valid configurations, then the fundamental constants of our universe are not uniquely determined by the theory. Instead, they represent one point among an almost incomprehensibly large collection of possible points, each realizable in principle. The landscape is not merely a theoretical possibility. In the eternal inflation framework, different regions of space correspond to different points in the landscape, with local physics determined by the compactification that occurred when inflation ended in that region. The string theory landscape and the inflationary multiverse are therefore closely connected, with the landscape providing the set of possible physical configurations and eternal inflation providing the mechanism by which different configurations are realized in different bubble universes. Leonard Susskind, a theoretical physicist at Stanford University and one of the original developers of string theory, introduced the term cosmic landscape to describe the full set of possible string theory vacua. Susskind made the case for the landscape framework in his 2006 book The Cosmic Landscape and in a series of technical papers published in the preceding years. His argument is that the landscape, taken in combination with the mechanism of eternal inflation, provides a natural and scientifically coherent explanation for why our universe has the specific physical constants it has, without requiring those constants to be uniquely determined by the underlying theory. The key move in Suskind's argument is the application of what is called the anthropic principle in a statistical sense. Given a landscape of 10 to the 500 possible configurations and a physical mechanism that realizes many of them in separate bubble universes, observers will only find themselves in configurations compatible with their existence. The constants of our universe appear to be finely tuned for life in Suskind's framework, not because the theory required them to be, but because observers can only exist in the rare configurations that permit life. The landscape framework is controversial within the physics community, with critics arguing that it renders string theory unfalsifiable and that the anthropic reasoning it requires is not scientifically useful. String theory has been under active development since the 1970s and has attracted a substantial fraction of the theoretical physics research community's effort during that period. Despite this investment of time and talent, it has not produced a confirmed experimental prediction. The supersymmetric partner particles that many versions of string theory require have not been detected at the Large Hadron Collider, which has searched for them at energies up to 13 TeV. The extra dimensions that string theory predicts have not been detected. No string itself has ever been observed or probed at any scale. The theory's characteristic scale, the Planck length, is too small by many orders of magnitude for any conceivable current experimental approach to reach. Physicists who continue to work on string theory generally acknowledge these limitations while maintaining that the framework has produced genuine intellectual progress, new mathematical tools, dualities between seemingly different physical theories, and the discovery of unexpected connections between quantum gravity and quantum field theory. Critics, including physicists Lee Smolin and Peter Voigt, have argued that the absence of confirmed predictions after decades of development is a significant problem, and that the physics community's investment in string theory may have come at the cost of alternative approaches. This debate remains ongoing. The cosmic microwave background is a bath of microwave radiation that pervades all of space and is detectable from every direction in the sky. It represents the oldest electromagnetic radiation that can be directly observed. In the first moments after the Big Bang, the universe was a dense, hot plasma in which photons were constantly absorbed and re-emitted by free electrons, making the early universe opaque to light. Approximately 380,000 years after the Big Bang, the universe had cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms. With free electrons no longer available to scatter photons, light was able to travel freely for the first time. The photons released at that moment have been traveling through space ever since, and we observe them today as the CMB. The expansion of the universe over the intervening 13.8 billion years has stretched the wavelength of this radiation from visible light to microwaves. The CMB carries an imprint of the physical conditions in the universe at the moment of its release and provides the most direct observational window into the early universe available to astronomy. The CMB was first detected in 1965 by Arno Penzias and Robert Wilson at Bell Laboratories, who were working with a sensitive microwave antenna and detected a persistent background signal they could not attribute to any known source. The discovery, which earned Penzias and Wilson the 1978 Nobel Prize in Physics, confirmed a key prediction of Big Bang cosmology. Systematic mapping of the CMB began with the COBE satellite, launched by NASA in 1989. COBE detected for the first time the tiny temperature fluctuations in the CMB that inflationary theory predicts, with variations of approximately 1 part in 100,000 across the sky. The WMAP satellite, launched in 2001, measured these fluctuations with substantially greater precision and produced detailed maps used to determine the age, composition, and geometry of the universe. The Planck spacecraft, operated by the European Space Agency and launched in 2009, produced the most detailed CMB maps to date, with data releases in 2013 and 2015. The Planck maps have been used to test cosmological models with unprecedented precision. The measurements are consistent with inflationary cosmology and have constrained or ruled out several specific inflationary models while leaving the general framework intact. If the eternal inflation framework is correct and our universe is one bubble among many, there is a non-zero probability that another bubble universe has collided with ours at some point in the past. Physicists have worked out the theoretical signature that such a collision would leave in the CMB. When two bubble universes collide, the collision boundary propagates into both universes at the speed of light. From within our bubble, the affected region would appear as a circular disk on the CMB sky, distinguished by temperature or polarization properties that differ from the surrounding CMB. The shape of the signature is expected to be precisely circular, a distinctive geometric feature that would be difficult to explain by other known physical processes. Research groups have conducted systematic searches for these circular signatures in CMB data from both WMAP and Planck. The analyses have set limits on the number and intensity of bubble collisions and have searched for candidates that meet the expected statistical and geometric criteria. The search is technically complex because the expected signal could be subtle and could overlap with other CMB features. No confirmed collision signature has been identified in the data to date. A confirmed bubble collision signature in the CMB would represent indirect but significant evidence for the eternal inflation framework and the associated multiverse. It would not prove the existence of all bubble universes predicted by eternal inflation, nor would it confirm the specific physical properties of the colliding universe. What it would establish is that at least one other bubble universe exists and has been in causal contact with ours. This would be the first observational evidence of any kind for any universe beyond our own. The evidentiary value of such a discovery would depend on how convincingly the observed signature could be shown to match the specific predictions of bubble collision physics rather than some other known or unknown effect. The signature must be circular, must have the predicted relationship between temperature and polarization, and must be located in a region of the sky that is otherwise consistent with standard CMB statistics. Meeting all of these criteria simultaneously would make alternative explanations substantially harder to sustain. The scientific community's response to such a discovery would likely involve intensive analysis across multiple groups to verify the signal before any conclusion could be drawn. No confirmed signature of a bubble universe collision has been identified in CMB data from any survey to date. Systematic searches using both WMAP and Planck data have not produced a candidate feature that meets all of the criteria expected for a bubble collision. This does not rule out the eternal inflation framework because the probability of a detectable collision depends on parameters that are not independently constrained, and it is possible that no collision has occurred close enough to our bubble to leave a detectable imprint. Searches have established upper bounds on the frequency and intensity of any collisions that might have occurred, and those bounds are consistent with the eternal inflation framework as well as with the absence of any collision. The CMB does contain several anomalies, features of the temperature distribution that are not cleanly explained by the standard cosmological model. These anomalies have been noted and studied by multiple research groups. Some physicists have suggested that one or more of them might be related to a bubble collision, but these suggestions have not been confirmed by analysis, and the anomalies remain in the category of unexplained statistical features rather than confirmed evidence of any specific physical process. The CMB cold spot is a region of the southern celestial sky, located in the direction of the constellation Eridanus, where the temperature of the CMB radiation is measurably lower than the surrounding area. The feature was first identified in 2004 using data from the WMAP satellite. It covers an area of the sky significantly larger than typical CMB temperature fluctuations and is colder than the statistical expectations of the standard cosmological model by an amount that, depending on how the statistics are calculated, has a probability of occurring by chance of roughly 1 to 2%. The cold spot has been confirmed by subsequent analyses of Planck data. Its existence as a real feature of the CMB is not disputed. Several explanations have been proposed for the cold spot. One leading conventional explanation is the presence of a very large void in the distribution of galaxies between us and the CMB surface, known as the Eridanus supervoid. Photons crossing a large void can lose energy through a mechanism called the integrated Sachs-Wolf effect. However, analyses of the Eridanus supervoid have suggested it may not be large enough or empty enough to account for the full extent of the cold spot. A bubble universe collision has been suggested as an alternative explanation, but this has not been supported by detailed analysis of the cold spot's properties. The cold spot remains without a fully satisfactory explanation within the standard cosmological model. The most conservative interpretation, held by the majority of cosmologists who have studied it, is that the feature represents a statistical fluctuation, an unusual but not impossible outcome in a universe where CMB temperature fluctuations are random. At a probability of roughly 1 to 2%, the cold spot is unusual but not implausible as a statistical accident. The supervoid explanation accounts for some of the cold spot's properties but does not fully match its observed characteristics according to several analyses. The bubble collision hypothesis has not been shown to produce a signature with the specific properties of the cold spot. As of the current state of the literature, the cold spot is formally classified as an unexplained anomaly in the CMB, meaning that no proposed explanation has achieved general acceptance. Future CMB surveys with greater sensitivity and resolution may provide data that makes it possible to distinguish more clearly between competing explanations. Until then, the cold spot represents an empirical puzzle without a definitive solution. The next generation of CMB observational instruments is expected to substantially improve the sensitivity and resolution of CMB measurements, which may in turn allow more definitive tests of various physical hypotheses, including the bubble collision scenario. The Simons Observatory, currently under construction in the Atacama Desert of Chile at an altitude of approximately 5,200 meters, is designed to measure CMB temperature and polarization with substantially greater sensitivity than previous experiments. The CMBS-4 project, which is in the planning stages, would deploy a network of high-sensitivity telescopes at both South Pole and Atacama sites to produce CMB maps with unprecedented signal-to-noise ratios. These next-generation experiments are primarily motivated by the search for primordial gravitational wave signatures in CMB polarization, which would provide evidence about the energy scale of inflation. However, they would also produce data useful for testing the bubble collision hypothesis. A bubble collision would leave a specific polarization signature in addition to a temperature signature, and the improved polarization sensitivity of upcoming instruments may allow better searches for this combined signature. Whether any such feature will be found is unknown. The absence of a detection in upgraded surveys would further constrain the parameter space available to bubble collision models. Physicists have studied the sensitivity of the universe's large-scale properties to variations in the fundamental physical constants. The results consistently show that even modest changes to constants, such as the gravitational constant, the fine structure constant, the strong nuclear coupling constant, or the cosmological constant, produce qualitatively different universes. In many cases, the differences are total rather than gradual. A universe with a slightly different value for the strong nuclear force may contain no elements heavier than hydrogen. A universe with a slightly different cosmological constant may either recollapse in a fraction of a second or expand so rapidly that no structures ever form. A universe with a slightly different gravitational constant may produce stars that burn out in millions of years rather than billions, leaving insufficient time for complex planetary and biological evolution. The sensitivity of large-scale structure to these constants is sometimes described as fine-tuning, a term used by physicists to note that the range of values compatible with a universe containing atoms, stars, and life appears to be narrow relative to the full range of mathematically possible values. This observation does not carry any implication about design or purpose. It is a statement about the physics of parameter sensitivity. The rate at which stars consume their nuclear fuel depends on the balance between gravitational pressure, which compresses the stellar core, and the outward pressure from nuclear fusion, which supports the star against collapse. The specific values of the gravitational constant and the nuclear force constants determine where this balance lies. In our universe, a star like the Sun burns hydrogen at a rate that gives it a total lifetime of approximately 10 billion years. This long lifetime is significant because the fossil record shows that complex multicellular life on Earth required approximately 4 billion years to evolve. A planetary system around a star that burned out in millions of years would have far less time for biological evolution to proceed. If the gravitational constant were substantially stronger than its current value, stellar cores would be compressed more tightly, raising temperatures and increasing nuclear fusion rates. Stars would be more luminous and would exhaust their fuel much more rapidly on timescales of millions rather than billions of years. This would dramatically reduce or eliminate the time available on any orbiting planet for the slow chemical and biological processes associated with life as observed on Earth. Atomic nuclei heavier than hydrogen contain multiple protons, which are positively charged and therefore electrostatically repel each other. The strong nuclear force overcomes this repulsion and holds the protons and neutrons of the nucleus together. The balance between the strong nuclear force and electromagnetic repulsion determines which atomic nuclei are stable. In our universe, this balance permits stable nuclei from hydrogen through to the heaviest naturally occurring elements, enabling the full range of chemical elements and the chemistry they make possible. If the strong nuclear force were reduced by a few percent, this balance would shift. Nuclei with 2 or more protons would become unstable. Helium and all heavier elements would not form. The universe would contain only hydrogen. Hydrogen can participate in limited chemistry, primarily with itself, and cannot form the carbon-based molecular structures associated with life. The absence of heavier elements would also prevent the formation of the solid planetary surfaces, mineral chemistry, and metallic conductors on which technological civilization depends. A universe with a significantly weaker strong nuclear force would therefore contain stars that fuse hydrogen but produce no nucleosynthesis of heavier elements and no chemistry beyond the simplest hydrogen-based interactions. The cosmological constant, also referred to as dark energy, is the energy density of empty space. In our universe, it has a very small positive value that causes the expansion of the universe to accelerate at late times. This small positive value allows the universe to form large-scale structure, including galaxies and galaxy clusters, during the billions of years before dark energy becomes the dominant component of the energy budget. If the cosmological constant were substantially larger, the accelerated expansion would have begun much earlier in the universe's history, when the density of matter was still high enough for gravity to be forming the first galaxies. A larger cosmological constant would drive the expansion of space faster than gravity could draw matter together, preventing the formation of any bound structures. The universe would consist of a uniformly expanding gas of particles that would never aggregate into stars or galaxies. Physicist Steven Weinberg made a quantitative prediction in 1987 using anthropic reasoning that the cosmological constant should not exceed by too large a factor the energy density of matter at the time galaxies formed, because larger values would prevent galaxy formation and therefore observers. When dark energy was discovered in 1998 and its magnitude was measured, the observed value was found to be in rough agreement with Weinberg's anthropic estimate, a result that several physicists have cited as limited support for multiverse reasoning. The apparent sensitivity of life-supporting conditions to the precise values of the fundamental physical constants has prompted some physicists to apply what is called the anthropic principle. The observation that our knowledge of the universe is necessarily conditioned on the fact that we exist as observers, and that we can therefore only observe universes in which observers are possible. The anthropic principle was formulated in its modern form by physicist Brandon Carter in 1973. It comes in 2 main versions. The weak anthropic principle states that our observations must be compatible with the existence of observers, a statement that is logically trivial but has non-trivial implications for what physical conditions we can expect to observe. The strong anthropic principle, which is more contested, makes claims about why the universe must be structured to permit life. In the context of the multiverse, the weak anthropic principle is used as a selection effect argument. If there are many universes with different physical constants and observers can only exist in a small subset of them, then the universes observed by any observer will necessarily have life-compatible constants. This argument is used to explain the apparent fine-tuning without requiring the constants to have been specially arranged. The anthropic principle acquires explanatory force in the context of a multiverse in a way that it does not in the context of a single universe. Applied to a single universe, the statement that the constants must be compatible with our existence is trivially true and provides no explanation for why the constants have the specific values they do. Applied to a multiverse containing many universes with varying constants, the anthropic principle becomes a genuine selection argument. If the multiverse contains universes with a wide distribution of constant values, and if observers can only exist in universes where the constants fall within the life-permitting range, then the constants measured by any observer will necessarily lie within that range, regardless of how unusual that range is relative to the full distribution. This is the same statistical reasoning applied when noting that the conditions on Earth are unusually well suited to life. The observation is unsurprising given that Earth is the planet from which we are making it. Physicist Steven Weinberg's 1987 prediction of the cosmological constant, mentioned in the previous fact, was made using exactly this reasoning. He argued that the value of the cosmological constant should not be much larger than is compatible with galaxy formation, because we are observers and galaxy formation is a precondition for our existence. In the inflationary multiverse framework, particularly when combined with string theory, the number of large spatial dimensions is not necessarily fixed at 3 across all bubble universes. The compactification of extra dimensions in string theory can, in principle, leave different numbers of dimensions large, depending on the configuration of the compactification. Different bubble universes could therefore have different effective numbers of large spatial dimensions. Whether 2, 4, or some other number of large spatial dimensions can persist in a stable configuration and support complex physics is a question that has been analyzed from multiple angles. Physicists, including Max Tegmark, have examined what changes when the number of large spatial dimensions is varied, and have found that most variations lead to qualitatively different physics with significant implications for the possibility of complex structures. This analysis provides one way of understanding why we observe 3 large spatial dimensions. In a multiverse where different numbers of dimensions are realized in different regions, observers will only form in regions where the dimensionality supports the conditions required for their existence. A universe with only 2 large spatial dimensions faces topological constraints that prevent the formation of certain complex structures. In 2-dimensional space, any object with an internal channel or tube, such as a digestive tract or a circulatory system, would necessarily divide the plane it occupies into disconnected interior and exterior regions. This makes it topologically impossible to have a through passage in a 2-dimensional organism without cutting it in half. The internal architecture of neurons, including the branching dendritic trees that allow individual neurons to receive inputs from many sources simultaneously, requires 3-dimensional space to accommodate the necessary cross-linking without intersections that would short-circuit the signaling pathways. The constraints are not limitations of biological engineering, but topological properties of 2-dimensional space that cannot be circumvented. A 2-dimensional universe could support chemistry and simple molecular structures, but the specific architectural requirements for information processing systems of the complexity associated with biological neurons and brains cannot be met in 2 dimensions. This is one of the reasons physicists note that 3 large spatial dimensions may be unusual among possible configurations in the degree to which they support complex physical and chemical structures. The inverse square law of gravity, which governs the force between massive objects in our universe, is a direct consequence of living in 3 large spatial dimensions. In 3 dimensions, the area of a sphere centered on a point grows as the square of the radius, and gravity dilutes across that surface, producing a 1/radius squared dependence. In 4 large spatial dimensions, the surface area of a hypersphere grows as the cube of the radius, producing a 1/radius cubed force law. This stronger distance dependence has a decisive effect on the stability of orbits. In 3 dimensions, orbital mechanics produces stable elliptical orbits in which a perturbed orbit returns to a nearby elliptical path rather than spiraling inward or outward. In 4 or more dimensions, this stability is lost. A planet in a slightly perturbed orbit around a star in a universe with 4 or more large spatial dimensions would either spiral into the star or escape from the system rather than settling into a new stable orbit. The same instability applies to electron orbits around atomic nuclei, since the electromagnetic force follows the same distance law as gravity. Atoms in a universe with 4 or more large spatial dimensions would be unstable, with electrons spiraling into nuclei. Both planetary systems and stable atoms require 3 large spatial dimensions. Analyses of the physics of universes with different numbers of large spatial dimensions consistently find that 3 is the only number that supports both stable atoms and stable planetary orbits. 2 spatial dimensions prohibit the complex topological architecture required by biological structures. 4 or more large spatial dimensions produce force laws that destabilize both atomic and gravitational orbits. Only 3 large spatial dimensions produce the inverse square force laws that support stable Keplerian orbits and stable Bohr-like atomic structures. This analysis does not prove that 3 dimensions were required or designed. In the context of the multiverse, it is simply the observation that observers dependent on complex chemistry and stable planetary systems can only form in bubble universes with 3 large spatial dimensions, and that this condition further restricts the set of universes in which observers like us can exist. The observation is one input into the broader anthropic selection argument about why we find ourselves in a universe with the physical properties we observe. The simulation hypothesis is the proposal that the physical universe we inhabit is not a fundamental physical reality, but a computational process running within a more fundamental substrate. The idea has a long history in philosophy, appearing in various forms in the work of René Descartes and other philosophers concerned with radical skepticism about the external world. In its contemporary scientific form, it has been discussed by physicists including Sylvester James Gates Jr. and Edward Fredkin, as well as by philosophers including Nick Bostrom, whose formal analysis of the hypothesis has been widely cited. The hypothesis is not a mainstream scientific proposal in the sense of being accepted or actively investigated by the majority of physicists. However, it occupies a position similar to other multiverse frameworks in that it cannot be ruled out by current physics, has been discussed by credible researchers, and raises genuine questions about the nature of physical reality. Unlike the inflationary multiverse or the many worlds interpretation, the simulation hypothesis does not follow from any established physical theory. It is motivated primarily by philosophical arguments about the expected behavior of technologically advanced civilizations and by certain mathematical observations about physical law. Nick Bostrom, a philosopher at the University of Oxford, published a formal version of the simulation argument in 2003 in the journal Philosophical Quarterly. Bostrom's argument is structured as a trilemma. He argues that at least one of the following 3 propositions must be true. First, that virtually all civilizations at our current level of technological development become extinct before reaching the capability to run large-scale simulations of minds or physical environments. Second, that virtually all technologically advanced civilizations capable of running such simulations choose not to do so. Third, that we are almost certainly living in a computer simulation. The logic of the argument is probabilistic. If advanced civilizations do run simulations and run many of them, simulated minds would vastly outnumber non-simulated minds. Any randomly selected conscious entity would then be far more likely to be simulated than to exist in base reality. Bostrom does not advocate for any of the 3 options as the most likely. He presents the trilemma as a logical structure that forces a choice between them and argues that examining the implications of each option raises important questions about the nature of intelligence, the long-term trajectory of technological civilization, and the relationship between computation and consciousness. The simulation hypothesis, if taken seriously as a possibility, has implications for the scale and structure of reality that extend beyond a single layer of simulation. If a technologically advanced civilization can simulate a universe with conscious inhabitants, there is in principle no reason why the civilizations within that simulated universe could not, if they became technologically advanced themselves, simulate their own universes. This leads to the concept of nested simulations, in which multiple layers of simulated reality exist within each other. The total number of simulated universes in such a hierarchy could be very large, limited only by the computational resources available at each level. Whether this process can continue indefinitely depends on questions about the relationship between computational capacity and simulation fidelity that are currently unresolvable. In the nested simulation picture, the distinction between base reality and simulated reality becomes complicated, because observers at every level would have equal reason to believe their universe is fundamental. The hypothesis raises genuine philosophical questions about the meaning of physical existence, the relationship between mathematics and computation, and the criteria by which we could, in principle, determine whether we are in a simulated reality. Sylvester James Gates. Jr., a theoretical physicist and professor at Brown University who specializes in supersymmetry and supergravity, reported finding a specific mathematical structure within the equations of supersymmetry that is of the same type as the error-correcting codes used in digital communications and information theory. The structure in question is a doubly even self-dual linear binary error-correcting block code, a specific type of code with well-defined algebraic properties. Gates found this structure when analyzing the mathematical relationships between supersymmetric partners in the off-shell formulation of supersymmetry. Error-correcting codes are designed and used in information technology to detect and correct transmission errors in digital data. The appearance of a mathematically identical structure in the equations governing supersymmetric particle physics is an unexpected and unusual finding. Gates has described this in lectures and interviews and has noted that the coincidence raises questions he has not been able to answer about whether it reflects something deep about the mathematical structure of physical law. He has consistently been careful to note that finding such a structure in the equations does not constitute evidence for any particular theory of physical reality. Sylvester James Gates has discussed the discovery of error-correcting code structures in supersymmetry equations in multiple public forums, including interviews, lectures, and written pieces. He has described the finding as personally puzzling and has said that he cannot identify a conventional explanation for why this specific type of algebraic structure should appear in the equations of fundamental physics. Gates has been explicit and consistent in stating that the finding does not prove or even strongly suggest that the universe is a simulation. The mathematical structure he found is a type that arises in information theory but that does not establish a direct connection to any computational process underlying physical reality. The significance of the observation remains undetermined. It may represent a deep mathematical relationship between the algebraic structures of physics and those of information theory that reflects something important about the nature of physical law, or it may be a mathematical coincidence that has no deeper significance. The fact that a physicist of Gates's expertise and standing found the observation worth discussing publicly is a reason to take it seriously as a puzzle, even in the absence of any established explanation for what it might mean. In 2012, Silas Bean and colleagues at the University of Bonn and the University of Washington published a paper examining whether a universe simulated on a discrete spacetime lattice of the type used in lattice quantum chromodynamics calculations might produce detectable signatures in the properties of high-energy particles. Their analysis suggested that a lattice structure underlying spacetime would impose a specific upper bound on particle energies and would produce a measurable anisotropy in the spectrum of the highest energy cosmic rays, a directional dependence in their arrival properties that would not be expected in a non-lattice spacetime. The prediction is in principle testable with sufficiently extensive cosmic ray data. This is one of the few proposals in the literature for an empirical test of the simulation hypothesis. Whether the universe is in fact simulated on a lattice, and whether a lattice simulation would necessarily leave this type of signature are both open questions. The proposal assumes a specific computational architecture that is not the only possibility. An advanced simulation might not use a simple spatial lattice and might not leave any detectable trace at currently accessible energy scales. The Bean et al. Paper is notable primarily for demonstrating that the simulation hypothesis is not necessarily untestable in principle, even if testing it in practice remains far beyond current capabilities. The simulation hypothesis, regardless of its scientific status, highlights a question that is relevant to all multiverse frameworks. The extent to which the physical reality we directly observe may be embedded within or produced by a more fundamental structure that we cannot directly access. This question is not unique to the simulation hypothesis. Quantum mechanics raises it through the relationship between wave function and observation. Inflation raises it through the relationship between our observable bubble and the surrounding inflationary spacetime. String theory raises it through the compactified dimensions that determine the physics we observe but are not themselves observable. The simulation hypothesis takes the question to a different level, proposing a non-physical foundation for physical reality rather than a physical foundation that is simply inaccessible. Whether or not the hypothesis is taken seriously as a literal possibility, it reinforces a conclusion that emerges from multiple independent lines of physics research. The universe as directly observed may represent a limited and conditional view of a larger physical reality, the full structure of which may not be accessible through any instrument or experiment operating within the observable domain. Under the many worlds interpretation, every quantum event that contributed causally to any outcome in a person's life also gave rise to at least one other quantum branch in which the outcome was different. Because quantum mechanics governs the behavior of all physical systems at the atomic and subatomic scale, and because biological processes, including neural activity, are fundamentally physical, the contingencies of a human life are embedded in a chain of quantum events. Each of those events in the many worlds framework branched the wave function. The branch in which one outcome occurred and the branch in which an alternative outcome occurred both exist within the universal wave function. This does not mean that every macroscopic event has a direct quantum branch, or that every decision a person makes corresponds to a single branching event. The relationship between quantum branching and macroscopic outcomes is complex and indirect. The statement is the structural one. The full wave function of the universe contains branches for all quantum outcomes that occurred at any causal point in any chain of events, including those that ultimately produced macroscopic differences in a person's history. In the many worlds framework, those branches are real physical structures, not counterfactual possibilities. The many worlds interpretation taken literally implies that any macroscopic difference in outcomes that can be traced through a causal chain to differing quantum events is represented by a corresponding difference between branches of the universal wave function. If the decision to take a particular path or say a particular thing depended in any way on physical processes at the quantum level, including the electrochemical activity of neurons, which is governed by molecular and ionic processes subject to quantum effects, then different outcomes of those quantum processes are represented in different branches. The entity in each branch is continuous with the same prior quantum state before the branching. Their memories, their physical constitution, their personality are identical at the moment of branching. After the branching, each follows a separate and independent trajectory through time. The word you, in this context, is an indexical term, referring to the entity in a particular branch. There is no single correct referent for you across branches. Each branch contains a separate entity with equal claim to continuity with the shared pre-branching history. This is not a philosophical consolation or a narrative construction. It is the direct physical implication of the many worlds interpretation's treatment of the universal wave function. In the many worlds interpretation, no branch of the wave function is more fundamental or more real than any other. The wave function evolves unitarily, treating all branches symmetrically. The branch we identify as our universe has no special physical status. It is simply the branch we find ourselves in. This symmetry means that any other branch of the wave function, including branches in which events unfolded differently, has exactly the same physical reality as the branch we occupy. An entity in another branch is not a copy in any meaningful sense. A copy implies an original from which the copy is derived. In the many worlds framework, both entities arose from the same prior state through the same physical process. Neither is derived from the other. Both are equally original. The consciousness of the entity in another branch is not a shadow consciousness or a lesser instantiation. By any physical criterion available, it is equivalent to the consciousness of the entity in this branch. The entities are distinct individuals who share a complete history up to the point of branching and diverge from that point. They are related to each other in the way that two individuals sharing an identical genetic background and identical experiences up to a given moment would be related. The same in all prior respects, separate from the branching point forward. The conventional understanding of personal identity involves a continuous, single thread of experience that persists through time. Within any single branch of the wave function, this narrative remains intact. An individual within a branch experiences their life as a continuous sequence of events, with memory connecting present experience to past states. The many worlds interpretation does not disrupt this within-branch continuity. What it changes is the relationship between the within-branch experience and the structure of the wave function as a whole. Viewed from outside any single branch, the entity referred to as a person at any given moment in time is not a point but a set, the collection of all branches that share that person's history up to that moment. Every branching event that occurred in that person's causal past produced a new member of this set. Every branching event in their causal future will produce further division. The result, over a lifetime, is a structure that is not a thread but a tree, with each node representing a branching event and each branch representing a complete individual with a complete life. The many worlds interpretation implies that this tree structure is the complete physical description of what we refer to when we speak of a person. David Lewis, a philosopher at Princeton University who worked primarily in the second half of the 20th century, developed a philosophical framework called modal realism, which he articulated most fully in his 1986 book on the plurality of worlds. Lewis was not working in physics and did not develop his position from quantum mechanical considerations. He was working within analytic philosophy of language, specifically on the semantics of modal expressions, words like possibly and necessarily that appear throughout ordinary and philosophical language. His analysis led him to the conclusion that the most coherent way to account for the truth conditions of modal statements is to treat possible worlds as concrete, physical realities of the same type as the actual world. In Lewis's framework, there is no ontological distinction between the actual world and possible worlds. The actual world is simply the world in which we find ourselves, an indexical designation analogous to here or now, not a mark of special ontological status. Every logically possible world exists, with the same degree of physical concreteness as our world. Lewis's conclusion was not adopted by the majority of philosophers, who found it counterintuitive, but it was taken seriously as a rigorous philosophical position and has remained influential in philosophical logic and metaphysics. The parallel between David Lewis's modal realism and the many worlds interpretation of quantum mechanics is frequently noted in the philosophical literature on the foundations of physics. Both positions hold that all possible outcomes of contingent events are physically real in separate worlds. Both deny that there is a special ontological status for the world we happen to occupy. Both produce a picture in which the observable universe is one element of a much larger structure containing all possible histories. Despite these similarities, the two frameworks arose independently from completely different motivations and through different methods. Lewis was motivated by problems in the philosophy of language and sought to provide truth conditions for modal statements. Everett was motivated by the measurement problem in quantum mechanics and sought to eliminate the wave function collapse postulate. The fact that they converged on structurally similar pictures of reality through independent reasoning has been cited by some philosophers as a reason to take both positions more seriously and by others as reason for caution, noting that the similarity may be superficial when the details are examined carefully. The relationship between modal realism and the many worlds interpretation remains an active topic in the philosophy of physics. The many worlds interpretation presents a challenge to standard philosophical accounts of personal identity. Most philosophical accounts of personal identity focus on continuity, either psychological continuity, the preservation of memories and personality, or physical continuity, the persistence of the same physical substrate through time. Both types of continuity are preserved within any single branch of the wave function, meaning that personal identity within a branch is unproblematic by standard criteria. The challenge arises when considering the branching itself. At a branching event, one person becomes two. Both successors satisfy the continuity criteria equally. Both have complete memories of the pre-branching period. Both are physically continuous with the pre-branching entity. Standard identity criteria do not provide a principled basis for saying that one successor is the original person and the other is not. This is the branching problem for personal identity. Several philosophical approaches have been proposed. One response is to revise the concept of identity to allow for branching. Identity becomes a relation that can hold between one earlier stage and many later stages. Another response is to abandon the idea that there is a determinate fact about which branch is really you. Philosophers working on the foundations of quantum mechanics have developed detailed positions on these questions, none of which has achieved consensus. Among physicists who accept the many worlds interpretation, the most common position on personal identity is that branching produces distinct individuals who share a common history rather than producing two instantiations of a single continuous person. On this view, the entity in each branch after a branching event is a new individual related to the pre-branching entity by a historical relationship, but not numerically identical to either the pre-branching entity or to the entity in the other branch. This position resolves the branching problem by revising the identity relation. Rather than treating identity as a one-to-one relation that must be preserved through time, it treats the pre-branching entity as the common ancestor of the post-branching entities, who are related to it but not identical to it. This is analogous to the relationship between a parent and a child, rather than the relationship between a person at one time and the same person at a later time. The entities in different branches are, in this framework, related to each other as branches of the same lineage, rather than as instances of the same individual. This account avoids the logical problems of trying to maintain numerical identity across branching and is the most common position among physicists who work seriously on the many worlds interpretation. In the many worlds interpretation, branching is not an occasional or special event. It is the universal and continuous mode by which quantum possibilities become physical realities. Every quantum interaction, every photon absorbed, every electron transition, every nuclear decay, every molecular bond formation or breakage produces a branch. Because quantum interactions occur in every atom of every physical system at all times, the rate of branching is many orders of magnitude larger than any number relevant to human experience. The human body alone, with its approximately 7 trillion cells and the quantum mechanical processes occurring within each cell's molecular machinery, would be the site of an enormous number of branching events per second. This continuous and pervasive branching is not preferentially associated with moments of significance or decision. A branching event occurring in a cosmic ray shower a billion light-years away is, in the many worlds framework, as real a production of new branches as a branching event in a human neuron. The association of the many worlds interpretation with questions about human choice and alternative lives is a consequence of human interest in those questions, not a feature of the physics, which treats all quantum events equivalently. The picture of the universe that emerges from the many worlds interpretation is one in which the branching of the wave function is a continuous and all-encompassing process, not a discrete series of events with pauses between them. The wave function of the universe evolves at every moment in every region of space, and this evolution continuously generates new structure in the form of branches that separate from each other through decoherence. The total wave function grows in complexity continuously. There is no state in which branching pauses or stops. There is no region of space that is exempt from the quantum interactions that drive branching. The process has been ongoing since the earliest moments of the universe, and the total number of branches that have been produced since the Big Bang is a number for which no familiar context exists. This continuous branching is a prediction of the many worlds interpretation rather than an interpretive gloss on it. It follows directly from the application of the Schrödinger equation to the entire universe without a collapse postulate. Whether this prediction is correct depends on whether the many worlds interpretation itself is correct, a question that remains unresolved in the foundations of quantum mechanics. The scientific status of parallel universes as of the current state of research is that their existence has not been confirmed and has not been ruled out. No observation has provided direct evidence for any parallel universe. No experiment has produced data that requires the existence of other universes for its explanation. At the same time, the theoretical frameworks that predict parallel universes, including the many worlds interpretation of quantum mechanics, the eternal inflation model in cosmology, and the string theory landscape, are each grounded in physics that is independently motivated and in some cases well confirmed in other applications. The uncertainty is genuine and is acknowledged by the physicists working in the field. The question of whether parallel universes exist is not one on which physics has produced a clear answer that is simply waiting to be communicated to a broader audience. The answer is genuinely unknown, and the debate among physicists about the theoretical and empirical status of the multiverse is ongoing, substantive, and unresolved. The debate over the scientific status of the multiverse is one of the most sustained and consequential in contemporary theoretical physics. Researchers on both sides of the debate are credentialed physicists with substantial publication records and institutional affiliations. Those who support the multiverse framework, including Max Tegmark, Sean Carroll, David Deutsch, Leonard Susskind and Andre Linde argue that it is the natural consequence of taking well-supported physical theories seriously, and that the failure to test an idea directly does not make it unscientific if it follows from theories that are themselves testable. Those who are critical, including Lee Smolin, George Ellis, Joe Silk, and, in some respects, the late Steven Weinberg, argue that the multiverse either fails to meet the standard requirement of falsifiability, or that accepting untestable theories into scientific discourse undermines the standards that have made physics reliable. The debate is not a dispute between mainstream scientists and fringe thinkers. It is a genuine disagreement among specialists about fundamental questions in the philosophy and methodology of science, including what makes a theory scientific, what evidence is required before a hypothesis can be taken seriously, and what obligations the physics community has to maintain connections between theory and observation. David Gross shared the Nobel Prize in Physics in 2004 with Frank Wilczek and H. David Politzer for the discovery of asymptotic freedom in the theory of the strong nuclear force. Gross has expressed concern about the scientific implications of the multiverse framework on multiple occasions and in multiple forums, including a notable exchange at a 2005 conference at Stanford University organized by Leonard Susskind. Gross's concern is not that the multiverse is certainly wrong. His concern is that if physicists accept that the physical constants of our universe are the result of anthropic selection within a landscape of possible configurations, they may conclude that there is no deeper theoretical explanation for why those constants have their specific values. This would foreclose research programs aimed at deriving the constants from more fundamental principles. Gross believes that such a deeper explanation may exist, and that giving up the search for it on the grounds that anthropic selection provides a sufficient account would represent a premature and potentially costly decision for the field. He has described this risk as making the multiverse a dangerous idea, not in the sense of being false, but in the sense of potentially discouraging the kind of foundational theoretical work that has historically produced the most significant advances in physics. Lee Smolin, a theoretical physicist at the Perimeter Institute for Theoretical Physics in Waterloo, Canada, has been one of the most consistent and detailed critics of the multiverse framework, particularly as applied to string theory. Smolin's argument has several components. The core objection is that a theoretical framework compatible with any observation, because it contains a sufficiently large landscape of possible configurations, provides no genuine scientific explanation for any specific observation. If string theory, combined with the anthropic principle, can accommodate any value of the physical constants, then the observation that our constants have their specific values is not explained by the theory, only rendered unsurprising. Smolin argues that genuine scientific explanation requires the theory to predict specific values, not merely to be consistent with whatever is observed. He has also raised procedural objections to the way the multiverse concept has been developed and promoted, arguing that it has been used to defend string theory against what would otherwise be considered falsifying evidence, specifically the absence of predicted supersymmetric particles. Smolin developed an alternative framework called cosmological natural selection, which attempts to explain the apparent fine-tuning of physical constants through a mechanism analogous to Darwinian selection among universes produced by black holes. Sean Carroll, a theoretical physicist at the Johns Hopkins University, has argued in multiple books and papers that the multiverse is not a speculative addition to established physics, but a direct consequence of established physics taken seriously. His position begins with the many worlds interpretation of quantum mechanics. Carroll argues that the Schrödinger equation, taken as a complete and universal description of physical reality without the addition of a collapse postulate, directly implies the existence of branching worlds. Rejecting the many worlds interpretation on the grounds that it implies parallel universes requires adding an extra element to the theory, namely the collapse postulate, that is not derived from any more fundamental principle. Carroll argues that this is the less parsimonious option. He makes a similar argument about inflationary cosmology. The mathematics of the inflationary model, combined with the dynamics of quantum fields, implies eternal inflation and the production of bubble universes, accepting inflation as a description of the early universe while rejecting the multiverse as a consequence requires selectively accepting some implications of the theory while rejecting others. Carroll argues that the appropriate scientific response to discomfort with a theoretical implication is to examine whether the theory is correct, not to accept the theory while denying its logical consequences. The dispute over the scientific status of the multiverse is in part a dispute about the philosophy and methodology of science. Physicists on different sides of the debate hold different views about what criteria a scientific theory must satisfy, what counts as evidence, and what the relationship between mathematical description and physical reality should be. The falsifiability criterion associated with Karl Popper holds that a scientific hypothesis must make predictions that could, in principle, be shown false by observation. Many versions of the multiverse fail to satisfy this criterion in any direct sense because the other universes predicted by the theory are in principle unobservable from within our own. Whether indirect evidence, such as a CMB bubble collision signature, or consistency arguments, such as the claim that the theory follows from independently confirmed physics, should count as sufficient is a genuinely contested question. The debate also touches on what it means for a theory to explain a phenomenon. If the multiverse explains the apparent fine-tuning of physical constants by invoking anthropic selection, is that the same kind of explanation as deriving the constants from a more fundamental dynamical theory? Different physicists give different answers to this question, and the disagreement reflects substantive differences in how they understand the goals and standards of the discipline. Several researchers have identified specific physical scenarios in which multiverse theories might produce observable signatures accessible to future experiments. The bubble collision scenario in the CMB discussed in an earlier section is one such case. If eternal inflation is correct and a bubble collision has occurred in our past light cone, future CMB surveys with enhanced polarization sensitivity may detect the circular temperature and polarization signature expected from such an event. Gravitational wave astronomy, which became observationally viable with the first detection by LIGO in 2015, opens a second potential window. Primordial gravitational waves produced during inflation would carry information about the energy scale and dynamics of the inflationary period. Detection of the primordial gravitational wave background by future space-based detectors such as LISA or by ground-based detectors with improved sensitivity would constrain the range of inflationary models and potentially distinguish between single-field and multi-field inflation scenarios with different multiverse implications. Quantum experiments probing the foundations of quantum mechanics may provide a third avenue. As quantum systems of increasing size and complexity become controllable in the laboratory, it may become possible to test predictions that differ between interpretations of quantum mechanics in ways that were not previously accessible. The Laser Interferometer. Gravitational Wave Observatory, or LIGO, detected gravitational waves for the first time in September 2015, observing a signal produced by the merger of two black holes approximately 1.3 billion light-years from Earth. Since that initial detection, LIGO and its European partner Virgo have observed dozens of gravitational wave events from compact object mergers. These detections represent a new form of astronomical observation, one that is sensitive to phenomena that produce negligible electromagnetic emission and that can probe regions of space-time inaccessible to conventional telescopes. The relevance of gravitational wave astronomy to multiverse theories lies in the potential to probe the physics of the early universe. Phase transitions in the early universe, analogous to the freezing of water, would have produced gravitational waves that permeate all of space as a diffuse background. The characteristics of this background, including its spectrum and amplitude, would carry information about the energy scale and nature of the transition. Future space-based detectors, particularly the Laser Interferometer Space Antenna, or LISA, which the European Space Agency plans to launch in the 2030s, are designed to detect this type of primordial gravitational wave background, potentially providing new constraints on models of the early universe and the conditions that may have given rise to the multiverse. Quantum computers exploit quantum mechanical effects, including superposition and entanglement, to perform computations that would be intractable for classical computers of any size. The behavior of quantum computers provides a testing ground for the foundational principles of quantum mechanics at a scale and level of control not previously available. As quantum computers grow in the number of qubits they can coherently control and in the depth of quantum circuits they can execute, they make accessible quantum systems of increasing size and complexity that can be used to probe questions about decoherence, the boundary between quantum and classical behavior, and the nature of quantum randomness. David Deutsch has argued that the operational behavior of quantum computers provides evidence for the many worlds interpretation on the grounds that the exponential speed-up of quantum computation is explicable only if quantum systems are effectively performing computations across multiple branches of the wave function simultaneously. Whether this argument is persuasive depends on contested questions about the interpretation of quantum mechanics. Independent of the interpretive debate, improvements in quantum computing capability will expand the range of quantum systems that can be studied experimentally, which may in turn provide data relevant to the foundations of quantum mechanics and to the empirical assessment of competing interpretations. The history of physics contains numerous cases in which theoretical proposals that were initially treated with skepticism or dismissed as physically meaningless were subsequently confirmed by observation or shown to be unavoidable consequences of established theory. The atomic hypothesis was proposed by ancient Greek philosophers and was treated for centuries as a useful conceptual device with no claim to physical reality. The definitive physical argument for atomic existence came from Albert Einstein's 1905 analysis of Brownian motion. Black holes were predicted by general relativity but were for decades considered artifacts of the mathematics rather than real physical objects. Einstein himself published a paper in 1939 arguing they could not form in practice. Observational evidence for astrophysical black holes accumulated through the latter half of the 20th century, and the first direct image of a black hole was produced in 2019. The Big Bang theory was named derisively by Fred Hoyle, who preferred the steady-state model. The discovery of the cosmic microwave background in 1965 provided strong observational support for the Big Bang and eventually led to the abandonment of the steady-state model by the physics community. These historical cases do not constitute evidence that the multiverse is real. They illustrate that resistance to theoretical proposals on grounds of implausibility has not always been well-founded. The successive expansions of the scientific picture of the universe share a common pattern. Each one revealed the scale and complexity of physical reality to be substantially greater than the previous consensus had assumed. The Earth was understood for most of human history as the center of the cosmos. The Copernican revolution placed it as one of several planets orbiting the Sun. Later, telescopic observations established that the Sun is one of hundreds of billions of stars in a galaxy. Edwin Hubble's observations in the 1920s demonstrated that the Milky Way is one of billions of galaxies in an expanding universe. Each of these expansions required revising concepts that had been treated as settled and required accepting a picture of the universe that was larger and more complex than the previous one. The current multiverse proposals represent a potential further extension of the same pattern. Our observable universe containing its 2 trillion galaxies and all the physics that governs them may itself be one element within a larger structure. Whether this extension is correct is not yet known. What the historical pattern suggests is that the observable universe is unlikely to be the full extent of physical reality, and that the boundary between the known and the unknown has consistently been located further out than assumed. The scientific investigation of whether parallel universes exist has produced concrete results even in the absence of a definitive answer. It has developed the theoretical understanding of quantum mechanics, inflation, and string theory. It has motivated new observational programs in CMB astronomy and gravitational wave detection. It has deepened the engagement of physicists and philosophers with foundational questions about the nature of scientific explanation, the relationship between mathematics and reality, and the limits of empirical inquiry. The question of parallel universes is one of a small number of scientific questions that sit at the intersection of physics and philosophy in a way that makes it genuinely impossible to separate the two. Pursuing it rigorously has required physicists to develop and articulate positions on questions that are not purely technical, including what counts as evidence, what makes a theory scientific, and how to reason about conditions that may be unobservable in principle. These are not peripheral questions. They are central to how science works and how it should work. The engagement with the multiverse question has contributed to making those methodological questions more explicit and more carefully analyzed than they would otherwise be. The scientific investigation of parallel universes remains open. No aspect of the question has been definitively resolved. The theoretical frameworks that predict other universes are active areas of research, with significant work being done on their internal consistency, their observational implications, and their relationship to each other and to confirmed physics. The observational programs that might produce evidence for or against them, including next-generation CMB surveys, space-based gravitational wave detectors, and large-scale quantum experiments, are in various stages of development. The philosophical debate about the scientific status of untestable theoretical predictions continues in the research literature and at conferences. What is clear is that the question of whether we live in one universe or many is among the most fundamental that physics has yet confronted. It touches on the structure of space-time, the foundations of quantum mechanics, the nature of physical law, and the limits of observational science. Researchers who work on it are doing so with the tools and methods of physics, and the question is being approached with the seriousness and rigor that its difficulty requires. The answer, if it comes, will likely require advances in both theory and observation that are not yet available. The work continues. Physics has not confirmed the existence of parallel universes. It has not ruled them out. What it has done is produce several independent lines of reasoning, each arising from well-tested theory, that point in the same direction. The debate among physicists about the multiverse is serious, ongoing, and unresolved. Some researchers view it as the natural consequence of taking the best available mathematics seriously. Others argue that a theory incapable of producing testable predictions cannot function as science in the traditional sense. Both positions are held by credible scientists. What is not in dispute is that the question itself has reshaped how physicists think about the structure of reality, the meaning of physical law, and the limits of what observation can establish. The science continues.